So how does quantum mechanics work? In general chemistry, we look at the outcomes of quantum mechanics all the time when considering atomic orbitals, but how does it actually lead us to uh, determine what atomic orbitals are like? In most general chemistry textbooks, there's a discussion of standing waves, and some include a particle in a box model. They all include a description for de Broglie wavelength, but we usually have to look in a physical chemistry textbook to actually see what's going on in the process of quantum mechanics. In this video, I'm going to give a really brief overview of the process of quantum mechanics. In my general chemistry book course, when I use the Atkins textbook, uh, we will begin by looking at de Broglie matter waves and how they lead to the description for a particle in a box. The application that we're interested in would be the energy for the particle in the box when it also has wave behavior, and we have then quantized energy levels. In this video, we're going to look at the same model, particle in a box, but consider that center path here and see where quantum mechanics takes us. There's a famous quote that I find amusing. So the physicist Louis de Broglie was sharing his theory that matter has a wavelength to it. And sitting in the front row, there were other physicists, Peter Debye and Erwin Schrödinger. And Debye commented, if something is a wave, it needs a proper wave equation. What's he saying here? He's saying, as physicists, we know a lot about waves beyond simply that they have a wavelength. We've studied waves in many different ways. What would it mean if we look more seriously at describing a wave and the implications? So that's what Schrodinger does. So Schrodinger is an expert with working with waves. So he comes up with this more complex equation for describing the wave behavior. We're going to try to dissect and learn some of the features in here and how this actually works. Here's a description from Atkins. It says, don't be put off by the thought that the wave functions that we're going to be working with, given by the Greek letter psi, are mysteriously complicated mathematical expressions. Some wave functions are very simple. An important one is simply sine x. That's going to be one that we explore here when looking at the description for a particle in a box. So Schrodinger's equation is used to calculate the wave function for any particle. Here's an important description of showing the Schrodinger equation. Let's look at a couple different features. This equation right here is the Schrodinger equation that has summarized several components to it. It's taken all of these terms on the left and given it the symbol h. So internally here, h bar, that's something we've seen before, which is shorthand for h over 2 pi. All of these terms right here that had both a kinetic energy and a potential energy, those are summarized by the symbol h. And on the right-hand side, E is representing the total energy. Psi here is the wave function. So within our description here at the bottom, you notice we have a wave function on each side. We have an operator. In this case, the operator is the symbol h. And the value in front of the wave function on the right-hand side is what's called an eigenvalue. So first of all, let's consider what does it mean to have an operator. We'll look a little bit at operator algebra. So let's say our operator is the symbol x. And what does it mean? It means take the function and just multiply it by x. So if this is the function we're looking at, when we take the operator, combine it with the function, this is where it would take us. What if our operator symbol d means take the derivative? So if we use that same function, the symbol of the operator and the function means take the derivative. There are more complex operators. One that we'll see later in this presentation, the Laplacian is a more complex one. It's now taking the derivative, and it's not just with respect to x, but it's involving x, y, and z. Let's go back to this one where our operator symbol d means that we want to take the derivative. So we'll work through a couple examples. So if this was our function and we use the operator d to take the derivative, this is how it works out. So if you don't recall, when we're taking the derivative of e to a term, we brought that as a constant in front, and the rest stays the same. So if we were to do the same thing for these other functions, take a second, see if you can complete that. It would follow this pattern. And notice in each case right here, these are novel. In each case, we have what would be an important special example. The new function that we get differs from the old one only by multiplication of a constant. This certainly doesn't happen every time we take a derivative, but it does in this case. This special case right here, this is leading to what's called an eigenvalue equation. Eigen for specific. The constant is called the eigenvalue, and the function itself that follows this pattern is called an eigenfunction. So the way that we're going to use quantum mechanics is we put together these parts of our plan, the postulates. So we're going to say that the state of the system is defined by a function, our wave function, psi, that contains all the information that we can know about it. Every physical observable is represented by a linear operator. The things that we can observe, we can get that information by using the corresponding linear operator. The measurement of a physical observable will give a result that's one of the eigenvalues. So we might ask, what's the most important observable that we might have or be interested in? Well, it's the total energy. The operator, in order to get the total energy, is called the Hamiltonian. And that's what's given the symbol H. We saw before within our Hamiltonian, it can include a term for the kinetic energy and a potential energy. So what we're going to do is, within our expression right here, we're going to ask about the energy. We want to know an energy. So in order to ask that question, we'll use the appropriate operator, which would be the Hamiltonian. And then the eigenvalues that we get, those are the allowed energies for the system. Here, if I jump over to hyperphysics for a second, here's its overview, its introduction to the Schrodinger equation. Same kind of thing. It's using an example where there's both a kinetic energy and a potential energy. It's discussing how those could be expressed as operators, and that those are then included in the Hamiltonian, where it's trying to figure out the corresponding allowed energies for the wave function that it was looking at. In this case, it was trying to determine the allowed energies for a quantum mechanic model called the harmonic oscillator. You have different operators depending on what you're trying to figure out. Again, from the Hyperphysics website, there's different operators that you can use in order to ask the wave function in order to get information about a physical observable. For our scenario that we're looking at, we're going to be interested only in the kinetic energy. And this would be the operator that's used for that. So if we go back to our picture here, our one-dimensional particle in a box, the way that we define that, the box is a length L. The walls of the box have an infinite potential energy. This is a way of trapping the particle now within this region right here. So it's going to have some position between 0 and L, and it won't have any potential energy, only kinetic energy. When we've looked at other 1D particles in a box, this was exactly the same scenario. So we don't have to worry about what does it mean to have infinite potential energy. This is just what does it mean to construct a box. So whether we were looking at a particle or a wave, this would be the description for the box that we're interested in. So we have our Hamiltonian then. The Hamiltonian will be what we'll use in order to learn about the energy. So we see here that the Hamiltonian could include both a kinetic energy term and a potential energy, but in the scenario we just set up, we don't have any potential energy. So the only part of the operator that we need to work with will be the kinetic energy part. So we'll have the operator for the kinetic energy act on the wave function. That will be equal to the energy and the wave function. So in order to solve for this, we need to ask ourselves, well, what is the wave function? What types of functions, if you differentiate them twice, reproduce themselves? We want to be able to get the eigenvalues for that. Two that come to mind would be the sine and the cosine. If you take the derivative of the sine, you get the cosine. Derivative of the cosine returns you back to the sine term. So in both of these cases, if they're differentiated twice, they reproduce themselves. So both the sine and the cosine seem like good candidates. In both cases, we had an operator, which involves making them differentiated twice. We had a possible function that would work, would return an eigenvalue and the function again. So that's what I mean when I say that they would both work for us. We have two independent solutions then for the Schrodinger equation. So the wave function can include both components. It can include a component involving the sine and a component involving the cosine. A and B are constants that would give weightings, relative weightings for both of these. What are the A and B values? We're going to use the boundary conditions to determine them. So let's look at the idea of boundary conditions. So first of all, when we're considering what wave function, sometimes you'll see the language that they say that they must be well behaved. What are characteristics that a wave function must have? So in order to be well behaved, it has to be single valued and it has to be continuous. If we look at that solid line right here, this is not a possible wave function because it's not single valued. For a given x, it could have different possible values for the function. Continuous, well, this dashed line is not continuous. So in order to be a wave function, it needs to be single valued. It needs to be continuous. How about positive and negative? Can it be both? Yep, turns out that when we look at our wave functions, when we solve for the hydrogen atom, our wave functions will both have positive and negative regions. How about the boundary condition? So when we put it in our wave function within the box right here, what were the boundary conditions? We said that at both ends right here, it has to have a value of 0. We can't have it result in a physically impossible description. We said in this case, at both of our ends, it's going to have the wave function is going to have a value of 0. So that constraint, that boundary conditions that we just add, helps us decide the relative contributions for the sine and the cosine. If we're going to say that it ends up being 0 at both points, what does that mean for the contribution from the cosine? It means there is no contribution from the cosine. The cosine may have worked mathematically, but it does not give us a physically meaningful solution. So we're left with saying that the wave function is going to be related only to the sine. So here would be a solution describing then the wave function as being a sine wave. We have particular increments here because we're going to be establishing a standing wave. With these constraints, our wave function goes to 0 at both ends of the box. And we have this leading term here which normalizes it, which ends up taking a given wave and making the probability of finding our particle somewhere within that 100%. So we had our Schrodinger equation. For a particle in a box, we were only interested in the kinetic energy. We saw that the sine function would work as the suitable wave function, differentiated twice, returned its value, returned the function. So we have now what would work for our wave function. One more feature is if we take our expression right here and solve for E, we can manipulate our terms, and we're back to exactly the same energy equation that we found when we used our simpler de Broglie wavelength description for our particle in a box. So this would be the path that we've just taken through to see how quantum mechanics works. Let me double back right here. We saw that the energy was the same as within the de Broglie model. Let's see how our wave function also gives us insight into the location. One thing that we looked at earlier when we were first looking at descriptions of waves and aspects of diffraction was what happens if we have a wave go through these two slits. Constructive and destructive interference takes place, and then on our screen here it would show bright and dark patches where the light would strike the screen. In a wave model, the intensity of this radiation was proportional to the square of the amplitude of the wave. This would be true if we're looking at light. In our particle, though, once we introduce the idea of wave particle duality, we would look at that same phenomena, but we would say that the intensity is proportional to the square of the number of photons present at each instant. So individual photons were striking the screen. It would result in this overall pattern. The important idea here is notice what we're doing with the wave. We're taking its intensity and we're squaring it. That's telling us the likelihood of where we are going to find the particle. That's what we're going to do with quantum mechanics. So the German physicist Max Born, this is his interpretation of what do we do with these wave functions once we get them. What do they mean physically? So in his interpretation, comes back to what we would have done here with light. We're going to square it, and then that will tell us the likelihood of finding the particle. So if we look at this representation here, the red line is the wave function. The red line is the wave function. This would be the lowest energy, n equals 1, n equals 2. In each case, then, if we square it, we get the blue function. That tells us now the likelihood of finding our particle in the particular box. That's what's shown up here at the bottom. So in this darker region, here or here, more likely to find the particle. How about with the n equals 1? More likely to find the particle in the center region. Take a second. What would it look like for the wave function and the square of the wave function if we had a 1D box of length L when n equals 4? What does the n equal 4 wave function look like? And how about if we square it? Take a second, make a sketch of that. This is what I think it will look like. So this is the PhET-Sim that allows us to look at a particle in the box. So here's a description of the box. Within the sim right there, we can have the wave function. And when we square it, the probability density. So within that particular sim, for each of the waves that we put in the box, it also can be represented squared as the probability density. So notice there's regions where the electron can be found, or the particle within the box can be found, in regions where it cannot be found. Clearly, this is at odds with what a classical description would be, because with a classical description, the particle's anywhere in the box. When we're looking at it within the with aspects of a wave description, that's no longer the case. So there's a lot of information on this particular slide that looks at features of what we've already been talking about. How to interpret the Schrodinger equation. What does it mean to have the Hamiltonian with both a kinetic and a potential energy term? Looking at a 1D model where we did not have any potential energy, solving for the wave function and the corresponding energy values. The wave functions then begin with n equals 1 to higher n values, the corresponding energies for those, and how we can now take a wave function, square it, and then use that to describe the probability density. Before we finish, let's take the same analysis and consider it for a 3D box. So within a 3D box, instead of just looking at our particle being along one axis, we're going to have 3 different axes that it could be along. Here would be the Hamiltonian with now our Laplacian, because that was accounting for not just along one component, but along three, the x, y, and z. So turns out within this we can break it out. Once again, we don't have any potential energy, so we're simply looking at the kinetic energy. We're simply looking at this first term here, but instead of having it solely along the x, we're now interested in along the x, y, and z. We've taken our wave function and we're going to look at its components independently along the x, y, and z. We've already solved for it when we were looking at it simply in one dimension. That was giving us our particular sine wave. Turns out that the framework here simply reproduces that. If we're in 3 dimensions, we would have this same kind of analysis, but one time it would be along the x, one time along the y, one time along the z. If we put those all together and expressed it in terms of the volume, this would be the overall wave function. And these would be then the allowed energy levels. Some of the energy levels are degenerate, meaning that we can independently choose values for the A, B, and C term. Let's say we're independently choosing values for the quantum numbers instead. The quantum number for the x, y, and z. And there's different combinations where the overall energy would be the same. So for example, we could have quantum numbers of 1, 2, and 2, or 2, 2, and 1. Those would be 2 different examples that give the same overall energy. What does it now look like to consider these standing waves if we have the 3 dimensions of a box? I find this to be a useful representation. So this would be the case when we have where the particle is found for the ground state, when each of our quantum numbers were 1. Higher in energy would be a value of 2, 1, and 1. We'd have different degenerate energy levels because 2, 1, 1 would be the same as 1, 2, 1 or 1, 1, 2. It would just change the orientation of where the particle is found within the box. And as you see, as the quantum numbers get bigger, we see that it begins to fill up more and more portions of the box. And sure enough, then it would eventually reach our classic limit, where if we have a really large number within this, it makes it appear that the particle is found everywhere within the box. Now, it's more difficult to represent standing waves when we have in 3 dimensions, it seems, relative to just having in 1. That's going to be one of our challenges when we move on to representations of standing waves for the hydrogen atom. That's what atomic orbitals are. Our standing waves are solutions to our Schrodinger equation in 3 dimensions. Now, if we look within here, I don't think we would say these are what our atomic orbitals look like. The reason that we have a difference, we will once again use the Schrodinger equation, but the solutions will include not just a kinetic energy, but a potential energy term. So our setup within this particular discussion, our particle in a box, we began with a 1-dimensional box, extended it to our 3-dimensional box. Our next step, if we want to get to considering atomic orbitals for the hydrogen atom, would be to do the same thing, but also consider a potential energy term being present.